to yet another class. I'm Dr. B, your chemistry teacher. Today we are going to be discussing the transition state theory. Okay, we'll talk about the transition state theory. The transition state theory. Now, do not forget that as part of your contribution to what I am doing, you have to subscribe to my YouTube channel, Dr. B Chemistry Classes. You have to leave your comments in form of questions or even appreciation. Questions will be attended to accordingly. You also have to like, you have to share, go to my Facebook channel, my Facebook page, and also follow Dr. B Chemistry Classes, and also leave comments, like, and share. Now we are going to discuss transition state theory. It's something that borders on chemical kinetics. You must have heard of chemical kinetics in the course of your lectures. Now, before we go on to talk about that, let us put up a diagram so it can guide us in our discussion. Now, we have an equation like this. Okay, we have carbon, we have bromine, hydrogen, another hydrogen there, and hydrogen here, and then we also have carbon. Okay, this time around we have bromine. Okay, okay, we have here we have hydrogen, and then we have a compound here. Then somewhere down here we have this. Let's say this time around we have bromine. Okay, we have hydrogen. We have hydrogen, and this is bonded to Nu. Okay, let's say we have this. Let's take this a little bit up. Okay, let's say let's bring the bit here. Nu, we have bromine, we have hydrogen, we have hydrogen, we have hydrogen. Okay, let's say we have this diagram here. Now with this diagram here, this of course is the reactant, and of course this is the product. Now at this state here is where we call the transition state. This is a transition state. Okay, now we have this. Okay, cut across. Now this is your energy. Okay, while this is your reaction parts. This is your reaction parts. Okay, now usually this is this structure is trigonal. Is trigonal bipyramidal. And this usually is tetrahedral, and this is also tetrahedral. This structure is also tetrahedral. Okay, now usually at this transition state is where you have the highest, energy. Okay. Now this is a typical diagram of an exothermic reaction. If you look at it here, you'll see that from here to here should be your activation energy. Okay, so this delta H here is negative because it is exothermic. Now what I want us to know is that you could have a reaction given to you as A plus B, and you have AB, and then you have product. This is a typical reaction that has a transition state. This is likened to what we have here. Now, what is the transition state theory all about? we have been hearing of transition state. What is the transition state theory about? Now, this theory is used both in chemistry and engineering. Chemical engineering, the makes of it, even those in mechanical engineering, makes of it. Now, chemistry will also make of transition state theory. What does the theory say? The theory is simple. It believes that for a product to be formed, there must be a very high energy that the reactant must overcome in order to have the product formed. That is to say, according to the theory, you cannot have a product being formed without the transition states. So, if the reactants are able to get to the transition state, which is the highest energy, or the point with the highest energy in every reaction, that is when you can now have a product being formed. Now, let us look at that. Let us look at it away from there. What that simply means is that the rate of reaction, the rate of every reaction, depends seriously on the concentration of the reactants that are able to do what? They are able to overcome this transition state. So it believes that if you have a chemical reaction, the reactants will be such that they must possess a certain energy or an amount of energy that is either equals to or it is more than the transition state energy before a product can be formed. Now, if you take a look at what we have here, now if you have this, it means that the reaction here simply means that you have this reacting with this. Certainly, there is going to be a substitution reaction where the bromine will be pulled out and this will now bind with this compound to give you a product. But from this reactant moving to this point where you have the transition state, there is a highest energy at this point. Of course, look at the energy increasing. There is a point of highest energy at this particular transition state. Now, when it gets to this point here, there must be a transformation of this particular compound in such a way that it generates another compound having energy enough to overcome the transition state energy before a product can be formed. And that is simple. And that is why you can see that at the beginning of the reactants, there is a tetrahedral structure in terms of the shape of this compound. But when it got to the transition state area, there is a transformation of these reactants into a trigonal bipyramidal, which means this is the shape it has taken at this point of the transition state with an amount of energy which is equals to or higher than the transition energy, which is the highest energy, in order to overcome this particular activation energy of the reaction to give you the product, which the product of course gets back to the tetrahedral. So you can see that the transition state theory does not believe that once reactants are formed, product is being formed. No, it believes that reactants will start their reaction but must get to a particular point in time where it meets the energy of the reaction of the system that is quite high. It must be able as reactant to overcome this energy before you can have a product being formed. And that's why we said that the rate of reaction depends on what? On the concentration of the reactants that achieve these states. What states? Overcoming the highest energy, the transition state energy, which of course is the energy of the system. Remember that the activation energy is simply what the amount of energy that a particular reactant possesses enough to do what? To surmount the transition state energy for a product to be formed. So if the energy of the activation energy of the reactant is not equals to or more than that of the transition state, product cannot be formed. And before it can, there must be a transformation of the reactant into a state where it possesses that energy that can overcome the highest energy of the system for the product to be formed. Now that is the way it's looked at. There is something important that we must learn here. That the transition state where it possesses a sort of quasi-equilibrium, let me put it that way, that this particular compound that is formed at the transition state is very unstable with partial bonds. We must know that this compound here is unstable with partial bonds, and can't be isolated. And the reason why this compound cannot be isolated at the transition state is because it has partial bonds and is unstable. So you cannot do what? You cannot isolate this compound. But it plays a major role in the calculation of the rate constant of this reaction. See how it plays out. Even though this compound may not be fully part of the product that is formed, it cannot be isolated because it's unstable and has partial bonds, but it plays a major role in the calculation of the rate constant. Now we also have to know that this transition state is also very, very important because it plays a major role in the calculation of the reaction rate. So for you to talk about the reaction rate of this particular reaction, the transition state plays a major role in the determination of the reaction rate or the rate of reaction. Why the transition state equation or transition state product that is one intermediate product that is formed plays a major role in the calculation of the rate constant. So this is how the transition state theory appears to look like. It believes that for any product to be formed, there must be reactants that possesses energy enough to overcome the highest energy at the transition state for a product to be formed. Now I'm sure we've learned something out of there, but there are assumptions to the transition state, and we can take a look at those assumptions to the transition state theory. Let's look at the assumptions to the transition state theory. We'll just look at the major assumptions to the transition state theory. Now, if we are looking at the assumptions, the first assumption of the transition theory discusses equilibrium assumption, and the second one, energy barrier, and then the third one talk about the transition state configuration, and then the last one talked about the classical motion. Now these are the four assumptions of the transition state theory. And with these assumptions at heart, you'll be able to understand the theory. Now, the equilibrium assumption simply says that there exists an equilibrium between the transition state and the reactants. Yes, and that this equilibrium is a quasi-equilibrium. Quasi-equilibrium in the sense that there is a formation and deformation of the transition states. So it believes that if you have an equation A plus B, there is a quasi-equilibrium. This is it. It believes that there is a quasi-equilibrium between the transition state and the reactant. That is what transition state assumption, the first assumption, it says, look, there exists a quasi-equilibrium between the transition state and the reactant. And what that simply means is that this particular transition state will always form and decompose. As it forms, it produces a product. It decomposes to maintain the equilibrium between the reactant and what? And the transition state. without that formation and decomposition, to maintain this equilibrium, then there is no way you have product form in any chemical reaction. That is number one. Now, the second one is the energy barrier. Just like we said, it believes that there is an energy barrier which you call the activation energy. Now, it believes that there is an energy barrier at the transition state, which is the highest energy that the reactor must overcome in order to do what? To get the products. And that is why we had mentioned earlier that the rate of reaction depends seriously upon the concentration of the reactant that will do what? Will be able to overcome the transition state, the energy barrier. So, the transition state theory believes that in its assumption, there is an energy barrier that must be overcome. Look at what we had before, that we have this, that at this point, there is an energy barrier, the highest energy. So this reactant must do what? Surmount this energy for product to be formed. Now the third assumption is transition state configuration. It believes seriously that there is always, at the transition state, there is a formation of a quasi-product, an intermediate product, and that this intermediate product is completely independent of the reactant and product. It is on its own. It has its own configuration and properties. And that is why from tetrahedra we have a bipyramidal structure. So it believes that there is a configuration for the transition state quasi or transition state intermediate product that is formed, and it is completely independent of the product or reactant. It is unstable. It is also having partial bonds and cannot be isolated. That is what is explained in the transition state configuration. Now, the classical motion, it believes that once the reactant, that is for this classical motion, once the reactant surmounts at the transition state, which is the highest energy, that energy barrier, a product will be formed that will be a consequence upon classical motion, such that that product cannot be affected again by the transition state. That is what this means. The classical motion controls the product that is formed. It cannot be affected again by the energy barrier or by the transition state. So you can see that once you understand the assumptions of the transition theory, then you have gotten every information you needed to know about the transition state theory. I'm sure that you've learned something much today concerning the transition state theory. You have to keep a date with me, because I am going to come up again with another class that we're going to look at the transition state equation, looking at simple methods and ways we can use to derive the transition state equation and liken it to the theory. Now, do not forget to share, do not forget to like, do not forget to subscribe my YouTube channel if you so much appreciate what I'm doing. Do not forget also to follow my Facebook page, Dr. B Chemistry Class, to like, to comment. If you have any question at all, leave a comment and we will treat it. Until then, it is bye for now.